Hi everybody. It's a pleasure for me to introduce Tech Tesfai. Some of you may have met him at the industry meeting. He joined my group in November last year. He received his PhD degree from EPFL in 2017 and just right away joined my group after his defense. He is one of those cyber people that know about power, which are the type of people that Kretzy likes. He joins my group and my activity on data analytics for intrusion detection, and I'll leave the floor to him to talk about our recent work. Thank you.
All right. Thank you, Anna, for the introduction, and thank you everyone for coming for my presentation on sensor data analytics for intrusion detection. The work I present today is done in partnership with our colleagues at Lawrence Berkeley National Lab. And going forward, I will follow this outline for my presentation. I'll start by motivating why we need cyber-physical intrusion detection, and then I will talk about reconnaissance activities, identification of reconnaissance activities using two levels, where I will mainly focus on the fog computing, where we do data analytics to identify reconnaissance activities at the network edge level, and then I will talk about one application where we do data analytics to identify malicious activity by having more inputs and doing the analysis at the central point, where we call this the cloud computing level. And then I'll conclude my talk by talking about the visions we have on how to extend our work on data analytics by including more input data to our analytic algorithms. So Murphy law states that whatever can go wrong will go wrong, and this applies to our state of beings in the cyber physical systems. No matter how many security measures we put in place, there will always be a cyber breach into the network, and that's what we have been seeing so far from the different reports we see, starting from the repeat attacks on the Ukraine power grid and the recent report on the power system breach in the US that we see from the FBI and Homeland Security. And all these attacks, what the attacks do is that they diverge the system to operate from its safe operating limits. And our focus, our utilities focus should be on how to detect this divergence from its operating limits and then put measures in order to identify these attacks and then put countermeasures to solve these attacks. So our approach for detecting these attacks is we propose an intrusion detection mechanism to first detect that there is an ongoing malicious activity. And we do this by leveraging the expert knowledge about the physical laws. That's it's a physical, cyber physical system. We need to have an expert level knowledge about the physical laws that govern the safe operating limits of the grid, and we need to incorporate this into the laws, into the rules we use to identify the malicious activities. And we use data input measurements, high resolution measurements from a micro PMU, from micro PMUs appropriately placed in the important locations in the grid. We also use data packets coming from SCADA measurements that give us the status information about key locations in the grid. And here I put a plot of measurements both from SCADA measurement device and from PMU measurements, and we can see that our PMU measurements manage to capture a surge in the current phasor that happens for a short time window, whereas our SCADA measurements that happen at a slower rate completely miss this surge in the current, and this surge in the current could potentially be a result of a reconnaissance activity that could be exploited later on. So our main purpose is to combine this information from the high resolution micro PMU data and then integrate it with the data we get from SCADA measurements to look for intrusion detection. But having said about intrusion detection, it's not really an easy job to come up with an efficient intrusion detection given those challenges. And the main challenge is we don't have micro PMUs at every point in the smart grid, thus we don't have a full observability of the grid. And the other challenge is we cannot collect all input data from all points in the grid and then process it at the central location, because that introduces latency and the malicious activity detection, we want it to happen in near real time. And also there is inaccuracy about the grid parameters due to the time varying nature of the grid, as well as the human errors that are introduced when we put the status of the different components in the grid. And most importantly, utilities hire cyber experts, but the cyber experts do not necessarily have an expert knowledge about the operating laws, the way the physical system operates. So it's very difficult to come up with appropriate rules that correlate data from the different points of the grid and then come up with the correct outputs after the analysis of the data to say what's the current security status of the grid. So given this challenge, what we propose is a hierarchical intrusion detection algorithm architecture, where we do data analytics at the network edge level, where we call this the fog computing level. And in this level, we are blind about the whole global view of the utility, but we focus on the data we have about the local operation of that network edge, and we do analytics using local rules that apply only to that locality. And this allows us to achieve a near real-time analysis of the data, and in our case, we implemented and achieved a 1 second delay to come up with a near real-time analysis. And this also allows us to do prioritization whenever we detect an event using this local analysis. We prioritize those packets that identify this event to send them to the cloud computing, and at the cloud computing, we incorporate more input source, and we are able to have a more refined conclusion about what kind of activity it is, and we also can be, we are also able to localize this event that happens at a certain location in the grid. So we have two components: the fog computing component at the network edge and the cloud computing component at the central edge, which encompasses several inputs from different locations. So our main work on this hierarchical intrusion detection is Reconnaissance activity detection using input sources. So let me first present on the work we have done on the fog computing or the network edge level. So as a case study, I will talk about reconnaissance activity identification on a normally open switch at the substation level. And this is really a critical component of the grid where an attacker could be interested to see if he's able to manage, if he's able to toggle the status of this normally open switch. And our job as an intrusion detection system, our job is to see if we can identify if there is a reconnaissance activity against this normally open switch. So to start with this intrusion detection system we use, let's first give some insight about the Thevenin parameters about the transmission, the substation location here. If we have an normally open switch at the substation where we have two transformers connected to it, the Thevenin impedance of the upstream or the transmission system is mainly dominated by the transformer impedance. And if we have the normally open switch closed, then the Thevenin equivalent impedance becomes half of what it would be if the switch is open, because we will have two impedances connected in parallel to each other. So our goal in this intrusion detection system at this location is to use a single PMU deployed at the substation, at the distribution side of the substation, and to use these measurements from the single PMU measurement to track the Thevenin impedance. And based on the value of the Thevenin impedance, we can decide whether this normally open switch is closed or open. So before going to how we do this using Thevenin estimation, there have been several work done on Thevenin estimation using linear square methods, and each one of these methods have their own pros and cons. But the way we formulate our Thevenin estimation algorithm has specific advantage, and our contribution in this work is we are the first to propose a Thevenin parameter estimation based reconnaissance activity identification method. And our online Thevenin estimation algorithm works both for a balanced case and unbalanced case of the grid. And also the algorithm we propose is a robust algorithm that works well for both stationary, for non-stationary and time-correlated data. Besides, most of the algorithms, the techniques for Thevenin estimation proposed assume that the Thevenin voltage phase angle is constant, which actually leads to inaccuracies in the estimation of the parameters. In our case, we didn't assume this phase angle to be constant. So going forward to the Thevenin equivalent circuit of the transmission as seen from the feeder at the distribution level, we can represent the whole transmission by equivalent Thevenin impedance and an equivalent Thevenin voltage. And this equivalent circuit can be captured using this equation, where we have the voltage phasor and the current phasor measured at the bus at the feeder on the distribution side, and the Thevenin parameter, the Thevenin impedance, and the voltage, the Thevenin voltage are unknown. So we cannot solve these two Thevenin unknowns using only this equation, but assuming that the transmission lines are transposed, we can convert this equation to this sequence domain equation, where we have the measurements of the voltage and the current phasors from the PMU, and we have the impedance representation at this one. So if we consider the balanced case and the unbalanced case of a grid, we have two different ways of solving the parameters for the Thevenin parameters. For the unbalanced case, we make this common assumption where we do the positive sequence impedance is equal to the negative sequence impedance, and this sequence domain representation allows us to have three non-trivial equations from which we can directly compute the Thevenin impedance and the Thevenin voltage by using only a single measurement from the single PME. Whereas for the unbalanced case, it's more complicated than that, because the zero sequence and the negative sequence are trivial equations. So the only non-trivial equation we'll have is the positive sequence, and we have two unknowns in the positive sequence. Therefore, we are not able to compute the values of the voltage and the impedance of the Thevenin. So what we do is we first assume that the resistive part of the Thevenin impedance is negligible, so we represent it only using the imaginary part. And this diagram gives us the phase diagram of the equivalent Thevenin circuit for a balanced grid. And we also assume the voltage phase angle at the bus on the distribution side is 0, and we report all other angles in relative to the voltage angle, to the voltage phasor. So since we didn't assume the voltage phasor angle to be constant, let's first, what we did is we assume A to represent the magnitude of the Thevenin voltage, and we use the cosine law to convert this equation to this quadratic equation, where we call this the residual equation. And in this equation, we have two unknowns: the voltage, the Thevenin voltage magnitude, and the reactance of the Thevenin parameter. And this, we cannot still solve it. So what we did is we take a measurement of M measurements from the PMU at that single location. And since we have enough dynamics on the distribution side, we take this M over determined homogeneous equations, which are quadratic equations, and we take the square norm of this vector equation and we minimize it to estimate the parameters of the voltage magnitude and the source impedance of Thevenin. So by formulating our system in this way, what we managed to achieve is, first, the assumption of the voltage phasor angle disappears, because by just considering the voltage magnitude here, we make the voltage phase angle to disappear from this unknown set of unknowns. And also, by reporting the phase angles of all the other parameters in relative to the voltage phasor angle, we also remove the effect of any off-nominal frequency in the equation, because that is equivalent to rotating all those phasors with the same off-nominal frequency. So by formulating our objective function to estimate the parameters as a quadratic least square method, which is unconstrained, we use the LMA or the Levenberg-Marquardt algorithm to solve this method. And the advantage of using the LMA algorithm is that it is actually good at handling case when the objective function Jacobian matrix is close to rank deficient, and it shows better performance compared to the Gauss method when we have a bad initial guess when we start the algorithm. So this is the LMA algorithm. So I will not go through the details of this LMA algorithm. It's suffice to say that the only difference, the main difference between the Gauss-Newton method and the LMA algorithm is that the LMA algorithm uses these regularization parameters, whereas the Gauss-Newton method doesn't use this regularization. And now, presenting the numerical results from our simulations, we first use for the unbalanced case where we showed we have enough non-trivial equations to directly compute the Thevenin parameters from a single PME measurement. We used the 34-bus system, and then we added this section to represent the transmission line where we have the Thevenin parameter transformer, and we have a single PME placed at the distribution feeder bus. And from this simulation, what we managed to observe is that we actually, the estimated value of the Thevenin impedance is very, very close to the actual value of the Thevenin impedance, which shows that our method actually successfully computes the Thevenin parameters from a single measurement of the PME. And for the balanced case, what we did is we used the 39-bus New England test case, and we create the dynamics by ramping the load at bus 16 by a 2% per second increase. And here we plot the estimated and the actual measurements, and we can see that the estimated measurement closely follows the actual measurements of the actual estimates of the Thevenin impedance. And we did this to actually apply it for a reconnaissance activity. So what we see here is, again, we assume there is a main transformer which is always connected, and the backup transformer where the switches are normally open. So if we follow again the Thevenin impedance when the transformer is open, then it will be the one on the red line. So when we have an open transformer, whereas when we have the closed switch for the backup transformer, then the Thevenin impedance will be half of what we would observe. And the blue line actually shows our estimates of the impedance, where it gets half of what it was whenever we close those switch for the backup transformer, which also means that we are able to estimate the values of the Thevenin impedance and conclude that whenever the impedance gets half, then we conclude that the backup transformer switches are closed. And then we compare this conclusion with the SCADA traffic, which reports about the status of the switch. And if there is a mismatch, we can conclude there is a reconnaissance activity going on, and we write the necessary alerts to report that. So that was a case study for the fog computing part. And now I'll present you reconnaissance identification on the cloud computing part.
Quick question. Why do you call this reconnaissance activity? It seems that they're actually closing across that second transformer. That's not reconnaissance.
Right. So actually what we want to show here is if an attacker, so the reconnaissance is not really what is the actual attack. If an attacker is able to see that he has control on the switching on and off of the substring transformer, then the attacker can actually leverage this and perform another activity, let's say destroying the main transformer, and then keeping the switch on the backup transformers always open. So this is about actually detecting whenever an attacker is trying to see he has control over this backup on this switch on the backup side.
So you're saying that the attacker is verifying that they can close that second transformer?
Exactly. They can close or keep it open. They just want to know if they have access and control on the status of this switch. And that's not necessarily the actual attack, but this is just a reconnaissance activity for an upcoming attack.
Okay.
Any other questions on this side? Okay, so going forward on the cloud computing part. So again, like I said at the beginning, our main purpose on the Reconnaissance Activity Identification on the cloud is to be able to use more input from more input sources, both from the micro PME side and from the SCADA side. And then by correlating the information we obtain from the two sides, we can decide if an event is happening because of a natural phenomena or due to a malicious activity. And again, for this, as a case study, what we use is the fault location, isolation, and restoration application. So we do use micro PME measurements and run our Fleischer algorithm to detect whether there is an event and whether there is a fault. And given that there is a fault, we also correlate this with the information we get from the SCADA system to say, yes, it's to be expected, and there is a natural phenomenon that caused this fault. Or if there is a mismatch, we say the event is there is a mismatch of conclusion both from the SCADA and from the PMU analysis, and we say that that would be a reconnaissance activity. So here what we did is, I will give you a toy example without going to the details of the Fleischer algorithm we used. And here we have this line diagram where we have a single PMU and all downstream lines are equipped with a fault detector, which reports the status of those lines where there is whether there is a fault or not. And from this PMU data analysis at the control center at the cloud computing side, we can detect that there is a fault. For example, if there is a fault at line 4.5, we actually capture this in a simulated environment where there is an upsurge of the current magnitude here, and we detect it from a single PMU placed appropriately here. And we assume there is an attacker sitting on the communication line when the fault detectors report their information about the presence of fault on line 4.5. The attacker managed to tamper with this data and reports as if there is no attack going on or there is no fault in this network. So the intrusion detection system in the cloud will see this match between the PME data analytics and the information reported using the SCADA package, and then the attacker can conclude that there is something wrong going on. So in this particular deployment, we have only a single PMU, and then there are several lines downstream. So we cannot exactly pinpoint where exactly the fault is happening, but at least we can say there is a fault, whereas the actual Fleischer algorithm we are implementing also goes a bit further, and it also does the fault localization, and it reports where exactly this fault is happening. And we also have those fault detector devices deployed at all the lines and report this. So it's more complex than this one. And this attack, this fault we see here actually can have two possible ways, where there is a natural phenomena that caused this fault, and still the attacker is sitting on the communication line and tampering with the reported data, and that's still bad enough. Or the attacker can actually actively be causing this fault on this line and then tampering with the packets that are being reported to the monitoring system and keeping the control and monitoring system blind about this presence if we didn't have any PME measurements that would show us otherwise. So that was, that's again a quick presentation of our cloud computing intrusion detection mechanism. Now I'll present about our grand vision about what could be achieved if we include even further input data to the intrusion detection system. So what I have presented for computing-based intrusion detection, that is very limited information about the specific location of the data, and we still, by incorporating the expert knowledge about the dynamics and the operating limits of the grid, we still are able to detect certain intrusion detection, certain reconnaissance activities. And by even including further information from different locations within the grid's limit, we still can incorporate more rules and come up with more refined information about the reconnaissance activity. And then our vision is, what if we could include more information beyond the borders of the utility and come up with a more, again, more information that will give us a system that can give us either an early warning system or more information about an anomaly that's already going on. So our vision again is to have an automated security information and event management system that accepts data from different sources. And the reason why we want to have an automated system is the reason why it's so difficult to secure today's power grid is because there are so many legacy devices that do not necessarily support security. And also the lifespan of those devices is in the order of decades, which makes it even more difficult to keep track of all the security patches and measures that need to be performed on each device. And there are so many already reports possible attacks, on those devices, or even on the more modern, more updated devices. So it's very difficult to perform manual operation on this to secure this grid. And also there is the weakest link, which is the human factor, who do not necessarily follow the security policies and do the necessary security operations to secure the grid. So that's the reason why automation is necessary. So what we would see a perfect security solution for a grid would be to follow this maxim where we say, if you know the attacker and if you very well know your system, you actually can be prepared for what's to come from the attacker side. So we would propose, ideally we would propose a continuous security mechanism where we keep track of every detail about our system, and also we get more information about what are the capabilities and what are the things that could be exploited by an attacker, and then look for information about any anomaly we observe in our system and match this one with the things we get from an external environment. And if there is any match, then we can fix this vulnerability that's being exploited by the attacker. And if there is no attack going on in our system already, but there is some information obtained which could be exploited in our system, but not yet, then we can use this one as an early warning system and fix that vulnerability and keep doing this. So that would be the ideal security solution for a utility. So by knowing our system, what we mean is we should be able to, a utility should prepare an inventory of all devices, including the legacy device and all the software that's running, all the ports that are open. And then we also perform, the utility also performs a regular pen testing operation to identify for any vulnerable devices. We can use Metasploit tools, or we can use localized Shodan API to see for any vulnerabilities in our system. And we can also collect more information from different parts of our system, including alerts that are raised from firewalls or log data about access controls in those different devices, and incorporate all this information and give it to our security information and event management system. And from the knowing the attacker side, what we can do, what we actually plan to do is we will look for information from the dark web by looking for any chatters regarding common tools that are known to be used for industrial control system breaching. For example, the black energy is reportedly to have been used in the Ukraine attack and also suspected to be used in the US grid breach. The Shamoon is also another malware used in other several industrial control system security breach. So if we observe any sort of abnormal chatter about these tools, we can actually suspect that there is likely going to be an upcoming attack, not necessarily against us, but we can say that there are possible indications of a possible attack somewhere, and this can serve us as an early warning system. We can also look for, since we have a list of our systems and the possible vulnerabilities in our system, we can look for chatters about the SVA number of vulnerabilities or zero-day exploits, which is basically what was used in the Ukraine attack. And we can again use this information to go back to our system and fix those vulnerabilities And so again, the difficulty is in the details. How do we implement this? How do we collect this huge source of data from different points and make sense of it and come up with an appropriate security measure to come with a better solution than a manual operation is what we plan to look into. And we'd be very glad to receive comments on this, or also possible collaboration would be very welcome. And with that, I finish my presentation today. Here are a few of the publications we did related to this work, and I'll be happy to receive some questions.
A reminder that you're on mute. If you have any questions online, take yourself off mute, please.
So, Tech, this is Tim Yardley at the University of Illinois. A quick comment slash possible question for you. So, a lot of what you guys were exploring is being commercially implemented and also part of efforts like the DARPA Radix program. How far along are you at this point on the work past the PMU aspect in terms of the centralization? Is that something that you guys are just kicking around as an idea, or is that something that you're actively researching and working on at this point?
So far what we have achieved is using the PMU measurements for fault location and identification and correlating that information with SCADA data. We haven't incorporated any external information, including the DARWCAPE data. That's actually an idea we have about continuing and expanding our work the future direction, but we haven't done much work on that so far. But on the cloud computing part, using only information from the micro PMU and the SCADA data, we have actually some results regarding the Fleecer vulnerability and identification with these two sets of data.
Yeah, and if I may add, there is a testbed running with real data in Lawrence Berkeley. So I don't know if that addresses your question, but the cyber physical network intrusion detection, it's an architecture that is running, that is designed the way Tech described. So he just gave you more details about some of the rules that are implemented there.
Yeah, I mean, I've talked with Sean about Sean Peisert about what's implemented on his side and sort of where they are in transitioning stuff. I think it's great work. The part that I'm sort of leaning towards pointing out is that there are companies that are implementing this as part of the DARPA Radix program, using their own techniques accordingly. That's an opportunity for potential tech transfer of the type of stuff that you guys have done already, or potentially other discussions where I might be able to secure you some additional funding towards that type of direction. But the key there is you know, what you guys, the ideas you have on terms of implementation are already being implemented by some companies. So just sort of bouncing that off you to think about.
Yeah, you can give us the context of these companies. I'm pretty sure the blueprints are not exactly the same, but you know, if they're interested in our work, or that would be great.
Sounds good. I'll reach out to you offline, Anna.
Thank you.
I have a question to ask Professor Badi. Can we go back to slide 22 where you are talking about the fault on in the system, which is the right actually.
So this
yes. Yes.
Okay.
My first question is to know, is your algorithm able to identify what type of fault did happen in on the feeder, or you are assuming that all the faults are symmetrical? I think in the beginning you said that these algorithms can go for symmetrical or as well unbalanced system. And the second part of my question is, why are you talking about the fault? Because when the notion of attack happens, mostly it's about closing opening, denial of service. Are you saying that the attacker is trying to simulate a fault through the power grid, and then you are taking the measurement of actual measurement compared to the information about the fault and make decisions? Yeah, that was my two questions.
Okay, I'm not sure if I got the first part of the question correctly, but so I will start with the second question. So the reason why, this is again a single example of what could be done. We just focused on the Fleecer application, and we look for mismatch between the SCADA and PMU measurements. Again, this is not necessarily the actual attack that's going on. Some of those reconnaissance activities could be performed only for a very short time window, and these attacks are detected using the high resolution measurements from the PMUs, but this may not be detected and captured by the SCADA measurements. So we are again looking for any possible mismatch between the two sets of algorithms, and this could be potentially, if it's a reconnaissance attack, good for us, good for the utility to know it ahead, to know that there is a malicious activity going on. And also the same thing, if it's an actual attack, an active attack that's going on, that's another advantage to know it using the more refined information to come up with a response mechanism, an incident response mechanism to that. So the Fleecer is just one possible example to apply our intrusion detection, but any centralized application where, let's say, for example, the state estimation algorithm, and an example where we can do again data detection at the intrusion detection application, where we look for any mismatch between the PMU measurements and what a SCADA at a slower rate would report to us, and see for any mismatch in this case too.
Now, of course, the fault detector is not causing the overcurrent. Here, the point is that the monitoring center, the supervisory control, was spoofed, doesn't have the correct status, of the fault detectors, because the surge in current should have resulted in a fault detector being raised. And instead the control center doesn't see it. So again, ATT&CK insisted this is the matter of finding discrepancy between the picture that is available at the supervisory control and what's happening physically. And in this case, you can make the hypothesis that the overcurrent was caused by some other switching event that the attacker has been able to access in other parts of this grid.
Thank you.
Does that answer the question?
Yes, yes.
Are there any other questions online? In the room? Good. All right, everybody have a great weekend. Take care.